All right, we're going to look at correlation and regression today. The objectives are as follows. Draw a scatter plot for a set of ordered pairs. Compute the correlation coefficient. Test the hypothesis. H0, rho is equal to 0. Compute the equation of the regression line and coefficient of determination. Before we move on to chapter 10, as usual, we're going to go over the synopsis of what we did last time.
Good afternoon, everyone. In chapter 9, we dealt with inferences about two populations. In other words, the test of hypothesis mainly. The first section, section 9.1, was about proportions, and the following formulas we have been dealing with. P1 versus P1 hat, P1 versus P2 hat, where P1 and P2 refer to the population, P1 hat and P2 hat refer to sample statistics. So P1 hat is x sub 1 over n sub 1, P2 hat is x sub 2 over n sub 2, and Q1 hat and Q2 hat are the complements. In order to calculate the test statistic, where Z is equal to P1 hat minus P2 hat over the square root of P bar Q bar over N1 plus P bar Q bar over N2, we need to calculate P bar, which is known as the pooled sample proportion, which combines the two samples. So the way you calculate it is P bar equals X1 plus X2 over N1 plus N2. Also, I want you to pay attention to the formulas. The second portion of the numerator, which is P1 minus P2, is calculated from the H0. It comes from H0, and it's always 0 for us. Calculate the confidence interval. It's P1 hat minus P2 hat plus minus E. The margin of error, which is calculated as Z alpha over 2 square root of P1 hat, Q1 hat over N1 plus P2 hat, Q2 hat over N sub 2. And as far as the test of hypothesis is concerned, the 4 steps discussed can be used. So when we deal with a proportion, the p-value method and the critical value method, you remember the p-value compares areas and the critical value method compare numbers. They are equivalent. However, in most cases, the confidence interval is also equivalent, except in this case, because the way we calculate the confidence interval, use P1 hat and P2 hat, whereas in the case of a test statistic, we use P bar and Q bar, therefore they may vary slightly. So, going to the second section, we deal with two means, X bar, if you will. Obviously, the requirements are extremely important as always. We're dealing with two samples that are considered independent. They are SRS, or simple random samples. And either we have a normal distribution or approximately normal, or n is large. How large is considered large? Both n values must be larger than 30. In many instances, number 30 is also okay, but we prefer a number larger than that. So as usual, the population standard deviation, sigma, in this case, we say sigma 1 and sigma 2, because we are dealing with two populations. If they are known, and normally that is not the case, then we can use the Z test, in which case we use the test statistic Z equals X1 bar minus X2 bar over the square root of sigma 1 squared over N1 plus sigma 2 squared over N2. Again, notice the second portion of the numerator, which is mu1 minus mu2, is 0 coming from H0. The confidence interval, X1 bar minus X2 bar plus minus E. The way E is calculated when sigma is given, it's Z alpha over 2 square root of sigma 1 squared over N1 plus sigma 2 squared over N2. And pay attention to the fact that when you want to calculate the E, you can use your calculation in the previous step using the test statistic. Now, if sigma 1 and sigma 2 are missing, they are unknown, then we have no choice but to go with the t-test. So, two situations. Number one, we have unequal variances. By the way, most often this is the case. We can't really assume the alternate method where sigma 1 and sigma 2 are equal is the case unless given to us. So, with unequal variances, the degrees of freedom has a complicated formula, and it's posted on PowerPoint. However, the way we do it, we choose the smaller of the two degrees of freedom. That means n1 minus 1 and n2 minus 1. Then it gives us the test statistic equals x1 bar minus x2 bar over the square root of s1 squared over n1 plus s2 squared over n sub 2. Notice the same confidence interval, that means x1 bar minus x2 bar plus minus e is used as before. However, the calculation of e, the formula for e is different, in which case is equal to t alpha over 2 s1 squared over n1 plus s2 squared over n2. So not only the z has changed to t, the sigma 1 has changed to s1, sigma 2 has changed to s2. In the last case, where we assume that sigma 1 and sigma 2 are equal, then we use the pooled sample variance. And the degrees of freedom would be the two degrees of freedom combined, which means n1 minus 1 plus n2 minus 1. So the test statistic is similar to the previous ones. The numerator is the same. As far as the denominator is concerned, we use S sub P. In other words, test statistic, T is equal to x1 bar minus x2 bar over the square root of S sub P squared over n1 plus S sub B squared over n sub 2. What is S sub P? It's really the average. And the way the average is calculated is really through the weighted average. That's why S sub P is n1 minus 1 times S1 squared plus n2 minus 1 times S2 squared over n1 minus 1 plus n2 minus 1. The formula needs to be fixed here, is plus n2 minus 1. S sub P is equal to n1 minus 1 times s1 squared plus n2 minus 1 over s2 squared. The denominator, n1 minus 1 plus n2 minus 1. The E is T alpha over 2. Add T alpha over 2 before the square root of S sub P squared over N1 plus S sub P squared over N sub 2. That one needs to be fixed also. When we are dealing with dependent samples, which means basically we are using the same population before and after is used. The best course of action is to calculate the difference between the two values, which we call it D. Whether we use the lowercase d or uppercase d makes no difference. It represents the difference. And then we can use the test of hypothesis using the t distribution of the previous chapter, which is the chapter dealing with one sample, t distribution or x bar. We can use that. So if you notice the way the formulas work here, when we write d bar, if you recall, x bar was summation of x over n. So d bar, whether it's uppercase d or lowercase d, depending upon the text that you're dealing with, the summation of d divided by n. T, if you recall, dealing with x bar, one population was x bar minus mu over s divided by square root of n. Now, instead of x bar, we use d bar. Again, what is d? The difference between the two values. What is the d bar? is the average of those. So T is calculated that way. The standard deviation uses the same formula used in the first few chapters. The summation of x minus x bar quantity squared now changes to d minus d bar quantity squared over minus 1, or the second formula that many times they find it easier for the sake of calculation, the square root of n summation of d squared minus the quantity summation of d squared over n times n minus 1. As you recall, the confidence interval was x bar plus minus e, and now it's d bar plus minus e. The margin of error was t alpha over 2 s over square root of n. It is still the same s, except the s in that chapter referred to the s among the x bars. In this case, is among the, in other words, those differences. You have a bunch of differences. You have to calculate the standard deviation as above. And so when the values are dependent, we use the test that is the t-test to take care of the business. In this chapter, finally, in chapter section 9.4, we dealt with two variances or standard deviations. First thing we discussed was the idea of the F distribution, because in order to do the test of hypothesis, we need the F distribution to come up with the critical value, or for that matter, if you want to calculate the test. So first, F distribution starts from 0 and goes to infinity. It can never be negative, and it is really not normally distributed. It is skewed to the right. It's positively skewed. And obviously, there are infinitely many different families, and it gets better and more normally distributed as n gets larger. However, it is always skewed. So when we go through the test of hypothesis for this case, the same 4 steps as mentioned before. One step that requires the calculation of test statistic uses the test statistic F equals S1 squared over S2 squared. Because of the limitation of the F distribution, we always choose the first group, the one with the higher standard deviation. Therefore, F distribution, the test of hypothesis results in a right tail test always. So to look up the value from the F distribution table, you need the choice of alpha because it's a very limited table. You also have 2 degrees of freedom. Degrees of freedom for the numerator, which comes from the first group, higher standard deviation, and the degrees of freedom for the denominator, which is n sub 2 minus 1. So n sub 1 is the sample size for the larger variance, and n sub 2 for the smaller one.
All right, thank you. We're going to look at the concept of correlation, the key concept. In addition to hypothesis testing and confidence interval, inferential statistics determine if a relationship between 2 or more quantities variable exists. A correlation exists between 2 variables when the value of one variable are somehow associated with the value of the other variable. A linear correlation exists between 2 variables when there is a correlation and plotted points look like a straight line. This section considers only linear relationships, which means that when graphed in a scatter plot, the points are approximately a straight line pattern, and method of conducting a formal hypothesis test that can be used to decide whether there is a linear correlation between all population values for the 2 variables. The linear correlation coefficient is denoted by R, is a number that measures how well paired sample data fit a straight line pattern when graphed. use the sample of the paired data to find the value of R, and then use R to decide whether there is a linear correlation between the two variables. Regression is a statistical method used to describe the nature of relationship between variables. That is possible, or that is either positive or negative, linear or nonlinear. These are the questions that can be answered using the regression. Are two or more variable related? If so, what is the strength of the relationship? What type of relationship exists? What kind of predictions can be made from the relationship? A scatter plot is graph of order pair x, y. X would be the independent variable, y would be the dependent variable. Discrete, straight line, or linear pattern, we say that there is a positive linear correlation between x and y, since as x value increases, the corresponding y value also increases. We say that there is a negative linear correlation between x and y when or since as the x value increases, the corresponding y value decreases. No discrete pattern, which suggests that there is no correlation between x and y. Distinct pattern, suggesting a correlation between x and y, but the pattern is not that of a straight line. And as you can see, the scatter plot showed on the right hand side shows that when we have a positive correlation, R is 0.859, as you can get close to 1, and negative correlation would be, in this case, is given to me as minus 0.09 perhaps here, and no correlation where R is equal to 0.074, and nonlinear relationship that would be like the R would be 0.002 or numbers like that. The question that we had earlier, are two or more variable related? If so, what is the strength of the relationship? To answer these two questions, statisticians use the correlation coefficient, a numerical measure to determine whether the two or more variables are related and to determine the strength of the relationship between or among the variables. Linear correlation coefficient, which denoted to R, measures the strength of the linear correlation between the paired quantitative X value and Y value in a sample. It determines whether there is a linear correlation between two variables. What type of relationship exists? There are two types of relationships, simple and multiple. In a simple relationship, there are two variables, an independent variable and dependent variable. In a multiple relationship, there are two or more independent variables that are used to predict one dependent variable. What kind of prediction can be made from the relationships? Predictions are made daily in all areas, for example, including the weather forecast, stock market analysis, sales prediction, crop predictions, gasoline price prediction, and sport prediction. Some predictions are more accurate than the other due to the strength of the relationship. That is, the stronger the relationship is between variable, the more accurate the prediction is. So let's take a look at this example. Construct a scatter plot for the data shown for the car rental companies in the United States for recent years. So in this chart here, the first columns we have different companies A through F, and the second columns correspond to their cars in 10,000s, and the last columns would be the revenues in billions. So step number one, we're going to draw and label the X and Y axis, and then simply plot each point on the graph. And we can do one by one, as we can see when X is equal to 63, 7 would be the corresponding number to that, and then we plot that. We can easily use our technology TI calculator to plot that for us. That's all we do, just list them, and we can use this keystrokes to see the plot as we did by hand. The correlation coefficient computed from the sample data measure the strength and direction of the linear relationship between two variables. There's several types of correlation coefficient. The one explained in this section is called Pearson product moment correlation coefficient, which is known as PPMC. The symbol for sample correlation coefficient is R. The symbol for the population correlation coefficient is rho. The range of the correlation coefficient is from -1 to +1. If there is a strong positive linear relationship between the variables, the value of R will be close to 1. If there is a strong negative linear relationship between the variable, the value of R will be close to -1. N is the number of pairs of sample data. Summation of x, is the symbol sigma means summation of x would be sum of all x's. Summation of x squared would be sum of x values that are squared. Summation of x and then a square, sum up the x values and square the total. Don't confuse between summation of x squared and summation of x and then a square. The first one, you would have to look at the sum of x values that are squared. The second one is you sum up all the x value and then you square it. Summation of xy indicates that each x value should first be multiplied by its corresponding y value. After that, you would sum them up. You just add them up. R linear correlation coefficient for the sample data, and rho is the linear correlation coefficient for the population of paired data. And as you can see, as you get closer and closer to 1, that corresponds to a strong positive linear relationship. As you get closer and closer to -1, that corresponds to a strong negative linear relationship. As you get close to 0 would be no linear relationship. Given any collection of sample paired quantities data, the linear correlation coefficient R can always be computed, but following requirements should be satisfied when using the sample paired data to make a conclusion about linear correlation in the corresponding population of paired data. Number one, the sample of paired XY data is simple random sample of quantitative data. Number two, visual examination of a scatter plot must be confirmed that the points approximated a straight line pattern. Number three, because results can be strongly affected by a presence of outliers, any outliers must be removed if there are known to be errors. The effect of any other outliers should be considered by calculating R with and without the outliers included. So the outlier can really give us a wrong conclusion here. In other words, requirements 2 and 3 are simple attempts at checking that the pairs of XY data have bivariant normal distribution. And this is an ugly looking formula for R, although it looks very complicated, but it's just a matter of time to calculate these values. And as far as we know by now, we should know what summation of xy means, and we looked at that earlier. You should know the difference between summation of x squared and summation of x and then squared, and we can look at some examples to practice that. Xz denotes the z-scores for an individual sample value of x. Z of y is the z-scores for the corresponding sample value y. This would be another way to calculate R. In some books, they show both of them, and the first one is what you usually see in most textbooks. R also can be calculated as a summation of z of x, z of y over n minus 1. And again, we're going to look at some examples to see how we calculate these. The table listed give pairs data values, use technology to find the value of correlation coefficient R for this data. As you can see, there are several technology can be used to obtain the same exact result for R, and you're probably going to use the TI calculator most likely, but the other technology, as you can see, exists to obtain the same results. So let's take a look at this example. We're going to actually calculate this, find R using the following formula, and we have our table here. So we're going to list up the data for X, that would be for the chocolate, and we have 5, 6, 4, 4, 5, and the corresponding value for the noble is Y would be 6, 9, 3, 2, 11, and as you can see in our formula, we need to find a sum of X. So we're going to add all these numbers on the first column, and that would be the sum of X. And the sum of Y similarly would be adding all the numbers on the second column, would give us 31. X squared, we need to sum those up because we need that as a part of our formula. Summation of X squared, we find X squared for each of them, and then we sum those, becomes 118. Similarly, we can find the summation of Y squared, so we find each Y squares, and then you sum them up, that give you 251. We also need to know the sum of XY, so we're going to multiply X times Y and list them up here and sum them up, that would be 159. So that's all we need to substitute into our formula. Notice that n is equal to 5, so it's not 10. We have 5 pairs, so n corresponds to each pair, and the rest of the numbers, as you can see, we calculated using this table. So basically, you just plug the number into your calculator and you would get 0.795, and that's the value of R. Again, you can use your calculator using these keys to obtain the same results. You get a lot more accurate results using your calculator. Let's take a look at the second equation I showed you earlier that can be used for the same example. For this example here, we need to find z of x and z of y. This formula has the advantage of making it easier to understand how R works. The variable x is used for chocolate values, and the variable y is used for the noble values. For sample value is replaced by its corresponding z-score. So in this example here, x bar, we know how to find x bar from the previous chapters. That would be summation of x divided by n, and in this case I give you 4.8, and you have to find a standard deviation s of x, and you should recall the summation of x minus x bar square over n minus 1. That's how you can find this number. And for x equal to 5, then z of x would be x minus x bar over s of x, and that would be this value here. We have to use the same formula for y bar and s of y similarly. And as you can see, this value here, we did it for one of those values. It turns out to be 0.23905. And if you look at the chart, the z-score for all the chocolate value, see the third column, and the z-scores for all the noble values, see the fourth column, are shown. And we just have to manually do each of these one by one using the same formula I showed you earlier, and you would get the summation of z of x times z of y is equal to 3.179749, and then you divide n minus 1 into that, and these are 10 pairs, so 10 minus 1 would be 4. Divide 4 into that, as you can see, you can get the same answer here as we use the longer formula. So these are two different formulas you can use to obtain R. Find the correlation coefficient for the given data. we're going to use the first formula here. And as you recall, we need to calculate x, y, x squared, y squared, and that can be found using this data, given data. And then we want to sum all those, so you can find the sum of x and sum of y and sum of xy and sum of x squared and sum of y squared. And then the next step is just simply substitute those values into this formula. And as you can see, why we really rely on the technology to find R, because a lot of calculations involved to do it by hand. And in this case, R would be equal to 0.982. That suggests that a strong positive relationship is really close to 1. Using p-value from the technology to interpret R, use the p-value and significant level alpha as follows. Now, p-value is when it's less than or equal to alpha. That means reject H0. That support the claim of a linear correlation. P-value is greater than alpha, does not support the claim of the linear correlation. Using a Pearson correlation coefficient table to interpret R, consider critical value from the table or technology as being both positive and negative. Now, correlation, if absolute value of R is greater or equal to critical value, that it implies that there is a sufficient evidence to support the claim of linear correlation. No correlation if absolute value of R is less than critical value, that implies there is not sufficient evidence to support the claim of linear correlation. Properties of linear correlation coefficient R would be between -1 and 1 if all value of either variable are converted to a different scales. The value of R doesn't change. The value of R is not affected by choose of X or Y. Interchange all X value and Y value, and the value of R will not change. R measures the strength of the linear relationship. It is not designed to measure the strength of a relationship that's not linear. R is very sensitive to outlier, as we discussed before, in the sense that a single outlier could drastically affect the value. So let's take a look at this example. Test the significance of correlation coefficient found in example 4. Use alpha is equal to 0.05 and R is equal to 0.982. So step number 1, H0, rho is equal to 0, and alternative hypothesis H1 would be not equal to 0. As you can see, that would be two-tailed test. And step number 2, find the test statistic. We use a t-distribution. We should all be familiar with that, and using the formula. Just to note that these two formulas are exactly the same. In some textbook, you would see this formula here, R times square root of n minus 2 over 1 minus R squared. As you can see, algebraically, you can manipulate these to be equal to each other. Now, degree of freedom would be n minus 2. So we can use the first formula here to substitute the value of Rn, and then you can find T would be 10.3981. Step number 3, find a critical value, and alpha is equal to 0.05. Degrees of freedom here is n minus 2. So T, you can use our chart. You should all know how to do that by now. Would be plus or minus 2.776. And this would be other method that you can use. Another method would be using a Pearson relation table. So in this case, T as R is given to us as 0.982, and the critical value from the Pearson, n is equal to 6 and alpha is equal to 0.05, and as you can see, R would be equal to 0.811, and as you can see clearly, you see us get the same exact results here. That would be as we did earlier with the other method. As you can see, the test statistics lies right on the rejection part, and so as using the Pearson correlation table here. And either way you look at this, we have to reject H0. The claim is true. So there is a significant relationship between the number of cars rental agents owns and its annual income. This would be another example here using the value of R is equal to 0.0801 from 23 pairs of data, shows on the next slide, and use the significant level of 0.05. Is there significant evidence to support a claim that there is a linear correlation between chocolate consumption and number of the Nobel Prize winner? So in this case, we have our step number 1 again, H0 would rho is equal to 0. Alternative hypothesis would be not equal to 0. That would be two-tailed test. And test statistic can be found using either of these two formulas. And we get equal to 6.1314. And critical value when alpha is equal to 0.05, n is equal to n minus 2. We can use our table, would be plus and minus 2.08. And as you can see, if you use the second method here, when you use the Pearson table, the value of n is equal to 23 doesn't really there. When you get past 20, it goes to the increment of 5. So between 20 and 25, we can see when n is equal to 20, R would be equal to 0.444, and when it's n is equal to 25, R is equal to 0.396. So our critical value should be somewhere in between this. Or if you use a technology, you can get the more accurate number here. But regardless, as you can see, the number would be right between these two values, and both give us the same exact conclusion that we did with the previous method. That would be reject H0. The claim is true. There's a sufficient evidence to support that correlation, that there is a linear correlation between chocolate consumption and number of the Nobel Prize winner. So interpretation of that would be interesting. Although we have found a linear correlation, it would be absurd to think that eating more chocolate would help you with winning the Nobel Prize. So that was the part that we had earlier to show that we get the same exact result when we find these values. The value of R squared is the proportion of the variation in R that is explained by the linear relationship between X and Y. Using the 23 pairs of chocolate Nobel data, we get R is equal to 0.081. What proportion of the variation in number of Nobel Prize winner can be explained by the variation in consumption of chocolate? So in this example, the solution would be when R is equal to 0.801, we have to find R squared, which would be 0.642. So we conclude that 64% of the variation in the number of Nobel Prize winner can be explained by the linear relationship between the chocolate consumption and the number of Nobel Prize winner. This implies that about 36% of the variation of number of Nobel Prize winner cannot be explained by the rates of chocolate consumptions. When the null hypothesis has been rejected for specific value, any of the following 5 possibilities can exist. There is a direct cause and effect relationship between the variable that is X cause Y. Examples would be water causes plant to grow, poison cause death, heat cause ice to melt. There is a reverse cause and effect relationship between the variables that is X cause Y, that is Y cause X. Suppose a researcher believes expensive coffee consumption causes nervousness, but the researcher fails to consider that the reverse situation may occur. That is, it may be that an extremely nervous person crave coffee to calm his or her nerves. The relationship between the variable may be caused by third variable. If a statistician correlate the number of deaths due to drowning and number of cans of soda drink consumption daily during the summer, he or she could probably find a significant relationship. However, the soft drink is not necessarily responsible for the death, since both variables may be related to heat and humidity. Number 4 would be there may be a complexity of interrelationship among many variables. The researcher may find a significant relationship between the student's high school grades and college grades, but there probably are many other variables involved, such as IQ, hours of study, influence of parents, motivation, age, and instructors. And number 5 would be when the relationship may be coincidental. It would be coincidence. A researcher may be able to find a significant relationship between the increase in number of people who are exercising and the increase in the number of people who are committing crime. But common sense dictates that the relationship between these two values must due to the coincidence. Correlation doesn't imply causality. We noted previously that we should use common sense when interpreting results. Clearly, it would be absurd to think that eating more chocolate would help win a Nobel Prize. Common errors involving correlation would be assuming that correlation implies causality, using data based on averages, ignoring the possibility of nonlinear relationship. Hypothesis: if conducting a formal hypothesis test to determine whether there is a significant linear correlation between two variables, use the following null and alternative hypothesis that use rho to represent the linear correlation coefficient of population. Null hypothesis: H0, rho is equal to 0. That would be no correlation. Alternative hypothesis: H1, rho is not equal to 0 would be the correlation.